Now that you've gotten some exposure to how to simplify radicals, let's talk about operations with radicals. So I'm going to be showing you how to add, subtract, and multiply, and we'll also talk about division just a little bit, and we'll talk about how to rationalize denominators because that's really important in algebra and higher up in trig and calculus as well. So let's start with multiplying because we already know the product rule. You know that to multiply two radicals together, you just put them under one radical and multiply what's under the radicals together. But that can lead to some pretty large numbers and you're just going to end up having to simplify anyway. So a lot of times it's easier to factor the radicands instead of multiplying them together to get a big number. And I'll show you what I mean by that in just a minute. Now remember that sometimes when we're simplifying radicals, we can end up with two of the same factor under the radical. And don't forget that that means that we have a perfect square, and that can be simplified as well. So now let's look at example 8 together, and we're going to be practicing multiplying radicals. And notice the instructions say multiply and write in simplest form. And remember that just means that we can't leave any perfect square factors under the radical. So we're going to start off pretty small here in part A. Here we have square root of 10 times square root of 6. Now I know that you know that we could multiply 10 times 6 together and get 60. So we could say that if we multiply these together we get square root of 60, and we could simplify 60. But what I want to do is show you how to break down these factors so that you never have to go to the large number. Because it's not so bad with 60. 60 is still pretty small for us. But if the numbers get very large, you don't want to have to do that multiplying. You're going to want to know how to simplify without going to the large number. So I want you to think about this while the numbers are small here. So let's write these numbers together under one radical. So square root of 10 times square root of 6 can be written all together under one radical like that. Notice I am not multiplying those numbers together. I do not want the numbers to get any bigger than they are. I want to break them down. So the 10 is going to break down into 2 times 5. And the 6 is going to break down into 2 times 3. Now I know you don't see any perfect squares here, but remember because we have a pair of 2's, together they are making a perfect square. Together these 2's are making the square of 2. So I'm going to just rearrange the numbers under the radical for you, and I'm only going to do this step on this part of the example, and then from here on we'll just automatically know that it happens and we won't write it down necessarily because it is kind of an extra step, and I just want you to see what's going on here. So if we rearrange these numbers, we can think of this as 2 times 2 times 3 times 5. Notice it's all the same numbers. 2 times 2 times 3 times 5. This is the square of 2. So when we do the square root of 2 times 2, we're going to get 2. And then under the radical, we'll still have 3 times 5, which we're going to write as 15. So I want you to notice where each of the numbers came from. We have this 2 here because we had 2 squared under the radical. We have this 15 here because the remaining numbers that we could not simplify from under the radical are 3 times 5. So that's where the 15 came from. Now let's try part B together. So in part B we have square root of 20 times square root of 15. We do not want to have to multiply these two numbers together because if we do, it's going to make a larger number. And then we would have to think about how to break down that larger number. But right now, the number is already in two parts, so we'll just break down these parts. So we're going to write this all under one radical because that's what the product rule does for us. Now the 20 I'm going to break down into 4 times 5, and you might say, well, why not use 2 times 10? But remember, we want to get a perfect square wherever we can. So 20 is 4 times 5, and I'm going to use that because 4 is a perfect square. Now 15 is 3 times 5. So now not only do I have a perfect square, but I also have a pair of 5's, and they represent the square of 5. And then I have this 3, which isn't matching with anything. So now let's do the square root one factor at a time. The square root of 4 is 2. And the square root of this pair of 5's is 5. Both of those come out from under the radical. And then this 3 does not have a whole number square root, so it is going to stay under the radical. So right now we have 2 times 5 times the square root of 3. But we know that 2 times 5 is 10, and so we're going to write this as 10 times the square root of 3. And now let's look at part C. So here we have square root of 42 times square root of 35. Now we would not want to have to multiply 42 times 35 because first of all it would take us a couple of minutes to do that, and second it would give us a huge number, and what would we do with that huge number? We'd just have to turn around and break it right back down. So there's no sense in going to the larger number. Instead we just want to break down the pieces that we have. So let's write the 42 times 35 all together under one radical, and of course 42 is 6 times 7. And 35 is 7 times 5. And notice that that gives us a pair of 7s here. So the square root of 7 squared is going to be just 7. And under the radical, we'll still have a 6 times a 5. So we'll have square root of 30 there. 6 times 5 is 30. So our final simplified answer here is 7 times the square root of 30. Now let's talk about the quotient rule for radicals. So just like we had a quotient rule for exponents, we have a quotient rule for radicals. If n is a natural number, so n is our index, so n can be any positive whole number, and the nth root of a and the nth root of b are real numbers, then we have this quotient rule. The nth root of a over b can be written with two radicals, so that you have nth root of a divided by nth root of b. So basically what we're saying here is that if you have a fraction under a radical, you can split that up and have a radical for the top and a radical for the bottom. Okay, so here in example 9, we are going to practice using the quotient rule. We're going to simplify each of these expressions, and we get to assume that all variables represent positive real numbers, which remember that just means we don't have to think about absolute value bars. Okay, so this first one is really simple. We have square root of 16 over 25. So if we use the quotient rule for radicals, we'll split this up so that it's square root of 16 over square root of 25, and we'll simplify each of these separately. So the square root of 16 is 4, and in the denominator, the square root of 25 is 5. And so the square root of 16 over 25 just simplifies to 4 over 5. In part B, we have square root of 7 divided by 64. So first let's use the quotient rule to split this up so that we have a radical in the top and a radical in the denominator. Now the square root of 7 is not a whole number, so the 7 is going to have to stay under its radical. But in the denominator, the square root of 64 is 8. So the denominator becomes 8. And we just have square root of 7 divided by 8. Now in part C, notice that we already have two radicals. So what we want to notice here is that just like we can use the quotient rule to split radicals up, we can also use the quotient rule to put two divided radicals back together. So this can be written as square root of 24 divided by 8. And we know that 24 divided by 8 is 3. So this quotient becomes just simply square root of 3. Now in part D, we have square root of x to the 5th times y to the 3rd, all divided by z squared. And the first thing we're going to do is use our quotient rule to split this up so there's a radical for the top and a radical for the bottom. And then we're going to just simplify these radicals. So notice that in the top, the x and the y both have odd powers. So remember how we handle that? We say x to the 5th is going to be written as x to the 4th times x. Y to the 3rd is going to be written as y to the 2nd times y. In the denominator, we already have an even power, so there's no need to split anything up. Now let's just go through and take the square root of each factor that is a perfect square. So the square root of x to the 4th is going to be x to the 2nd. This x is going to stay under the radical. The square root of y to the 2nd is going to be just y, and this y is going to stay under the radical. And so I'll go ahead and put that square root of xy there. This x came from here, and this y came from here. And then in the denominator, the square root of z to the 2nd is just z. Now we're going to move on and talk about how to add and subtract radicals. This is really simple to do. When you're adding and subtracting radical expressions, it's exactly the same as combining like terms. Adding and subtracting radical expressions is very similar to combining like terms. Radicals can be combined only if the radicands are the same and if the radical indexes are the same. Just the same as when we're combining like terms, we can only do it if the variables match and the powers on the variables match. This is the same idea. Radical terms can only be combined if the radicands are the same and the indexes are the same. And to combine radical terms, all we have to do is add or subtract their coefficients. Of course, after you add or subtract the coefficients, the radicand will stay the same. So let's look at example 10 together, and our instructions say add or subtract to simplify each radical expression. Assume all variables represent positive real numbers. So here we go. Here we have 4 square root of 2 plus 3 square root of 2. Now imagine if this square root of 2 were an x. You would not have any problem saying 4x plus 3x is 7x. And here it's just the same. So 4 square roots of 2 plus 3 square roots of 2 gives us 7 square roots of 2. And of course, with the number written next to the radical like that, it's multiplication. So 4 times the square root of 2 plus 3 times the square root of 2 equals 7 times the square root of 2, but we usually omit the times when we're reading this. So now on part B, we have 2 square root of 3 minus 5 square root of 3. Now if we look at the radicals, we can see that they are the same. The radicands are the same, the indexes are the same, so these can be combined. And looking at the coefficients, 2 minus 5 is negative 3. So this one's going to be negative 3 square root of 3. On part C, we have 3 square root of 24 plus square root of 54. And you can see that these are different radicands. So we're not going to be able to just combine 3 and 1 and get 4 because we don't have like radicals here. So we'll need to simplify these radicals. Never decide that you can't add radicals until you have all the radicals fully simplified. So in this case, we know that 24 can be written as 4 times 6, and we know 54 can be written as 9 times 6. Now when we simplify this first radical, the square root of 4 is going to be 2, and that's going to come out here, and it's going to get multiplied by this 3, but in this first step I'm going to keep them separate. So I'm going to have 3 times 2, and the 2 came from the square root of 4, and then this 6 is going to stay under the radical. And then on the next radical, the square root of 9 is 3, so the 3 will come outside the radical and the 6 will stay under the radical because the square root of 6 is not a whole number. Alright, now back to this first term. 3 times 2 is 6. So what we have here is 6 square root of 6 plus 3 square root of 6, and of course 6 plus 3 is 9, so we end up with 9 square root of 6. In part D, we have 2 times the square root of 20x minus the square root of 45x. And again, notice that right now we cannot do this subtraction because these radicals are different, but we can simplify each of these, and if they're the same when we get done simplifying, then we can combine them. So 20x can be written as 4 times 5x. Now the x can go with either factor, but I put it with the 5 because the 4 is about to get simplified and it will no longer be under the radical. And then 45x can be written as 9 times 5x. Okay, so now back to this first radical. The square root of 4 is 2, and that's going to come out here. So I'm going to have this 2, and then I'm going to have the square root of 4, which is going to make another 2, and then this 5x will stay under the radical. And then we'll have minus the square root of 9, which is 3, times the square root of 5x. So the square root of 9 that you see here became 3, and then this 5x stayed under the radical. Alright, now back to the first term. 2 times 2 is 4. So we have 4 square root of 5x minus 3 square root of 5x, and of course 4 minus 3 is 1. So we end up with 1 square root of 5x, but remember we don't have to write the 1 when 1 appears as a coefficient. Alright, now on part E, we have 2 square root of 3 minus 4 square root of 5. Both of these radicals are fully simplified, and they are not the same. So this is an example of an expression that cannot be simplified. Now that we know how to add and subtract radicals and we already know the product rule for radicals, now we can talk about how to multiply radical expressions. So we can have binomials that contain radicals, and we want to learn how to multiply those types of things together. You can either distribute or use the FOIL method as needed. And so let's go ahead and get started here. This is example 11. It just says find each product. So in part A, we have square root of 5 times 2 plus the square root of 6. So we'll be distributing this square root of 5. Square root of 5 times 2 is going to be written as 2 times the square root of 5. And then square root of 5 times square root of 6 is going to be written as square root of 30, because 5 times 6 is 30. Notice that 30 does not contain any factors that are perfect squares, and so this radical cannot be simplified. And now, since this first radical and this second one are different, they cannot be combined. So this is our final answer. On part B, we have 4 times the square root of 12 minus the square root of 27. And of course, we are going to need to distribute the 4, but I think it'll be best for us if we first simplify these radicals. It doesn't matter whether you simplify the radicals first or last, but it has to be done at some point. So let's go ahead and think of 12 as 4 times 3, and let's think of 27 as 9 times 3. Okay, now the square root of 4 is 2, so that 2 is going to be written outside the radical. So we're going to have 4 times 2 square root of 3, and then on the second radical, the square root of 9 is 3, so that 3 is going to come outside the radical, and we'll have minus 3 square root of 3. Now at this point, we could go ahead and combine these two terms inside the parentheses, but let's go ahead and distribute the 4. So 4 times 2 square root of 3 is going to be 8 square root of 3, and 4 times 3 square root of 3 is going to be 12 square root of 3. So now we have 8 square root of 3 minus 12 square root of 3. Of course, the radicals are the same, and all we have to do is add the coefficients. So 8 minus 12 is negative 4, and we end up with negative 4 square root of 3. Now in example 12, we're going to be multiplying together binomials that involve radical expressions. So in part A, we have square root of 5 plus 3 times square root of 6 plus 1. So we are going to be using the FOIL method on this, and we'll just multiply our radicals and use our product rule as we go. First times first is going to be square root of 5 times square root of 6. Of course, you know that's going to be square root of 30. Okay, now we know that can't be simplified as well. Outer times outer is going to be square root of 5 times 1. That would be written as just square root of 5. Inner times inner is going to be 3 times square root of 6. So we'll write plus 3 square root of 6. And last times last is 3 times 1, so that's just plus 3. Now look at your radicals and see if any of them can be combined. They're all different in this case, so none of them can be combined, and this has to be our final answer. On part B, we have 7 minus square root of 3 times square root of 5 plus square root of 2. So same thing, this is 2 terms times 2 terms, so we'll need the FOIL method. First times first will be 7 times square root of 5, so we'll just write it exactly that way. Outer times outer will be 7 times the square root of 2, so it's going to be plus 7 square root of 2. Inner times inner will be negative square root of 3 times square root of 5, so that's going to be minus square root of 15. And last times last will be negative square root of 3 times positive square root of 2, so that's going to be minus square root of 6. And again, notice that all 4 radicals are different and none of them can be simplified, so we can't do any combining here, and this has to be our final answer. Now continuing with example 12, we have part C. So we have square root of 10 plus square root of 3 times square root of 10 minus square root of 3. And again, we'll use the FOIL method on this, and when we get to the end, I'm going to show you a couple of shortcuts for this type of problem. So let's apply our FOIL method, and we'll have square root of 10 times square root of 10. Of course, that's going to be square root of 100. Outer times outer is going to be minus square root of 30. Inner times inner is going to be plus square root of 30. And last times last is going to be minus square root of 9, because 3 times 3 is 9. Okay, now let's go back and simplify what we can. The square root of 100 is 10. The two middle radicals will not simplify, but notice that we have negative 1 square root of 30 plus 1 square root of 30. So they are going to add up to 0. So we won't have this middle term appearing in our final answer. And then for the last term, we have minus square root of 9, and that's going to be just minus 3. And this is going to be something we can complete. 10 minus 3, of course, is 7. Now, was there an easier way than writing out all of this? I think the answer is yes. So let's go back and talk about this. The first thing I would want you to notice when you look at a problem like this is that we have a sum and a difference of the same two terms. So we know in advance that the middle term is going to add up to 0. The second thing I want you to notice is that when you multiply a radical times itself, you pretty much just remove the radical. So if we go through this and use the FOIL method and remember that the outer and inner are going to add up to 0, first times first is square root of 10 times square root of 10. So that's a radical times itself, so it just removes the radical. The outer and the inner are going to add up to 0 because we have a sum and difference of the same two terms. And then last times last is positive square root of 3 times negative square root of 3. So we're going to have a minus sign there because these signs are different. And a radical times itself just removes the radical. So we can know that last times last is just going to be 3. And then we get the 10 minus 3, and of course we know that's 7. So you see how we really can skip this step altogether if we think about what we're doing. Let's look at part D. So here we have square root of 7 minus 3 all squared. I'm going to write this out times itself. Remember, squared means we multiply that thing times itself. So notice in this case we don't have a sum and difference of the same two terms. We have the same sign in both parentheses, and that's different from what we had over here in part C. So remember, when the signs were different, we lost our middle term. But when the signs are the same, we are not going to lose that middle term. So let's apply the FOIL method here. So square root of 7 times itself is just going to be 7. Outer times outer is going to be minus 3 times the square root of 7. Inner times inner is also minus 3 times the square root of 7. And then last times last is negative 3 times negative 3, so that's positive 9. And now let's see what we can do here. We'll want to combine any terms that can be combined. So I notice that 7 plus 9 is going to make 16. And then negative 3 square root of 7 minus 3 square root of 7 is going to make minus 6 square root of 7. And so that one's finished. Now I want to caution you against a mistake that I see a lot of students make. A lot of students will try to say 16 minus 6 is 10, and they'll try to put 10 square root of 7 as the final answer. But we cannot do that because remember, this 6 is not free. This 6 is being multiplied by square root of 7. And remember, multiplication takes precedence over subtraction. Remember your order of operations. So we can't do this subtraction because these are not like terms, basically. So we have to leave it in this form. Now we need to talk about how to rationalize denominators. So a simplified radical expression never has a radical in the denominator. We never leave a radical in the denominator of our final answer. And also a simplified radical never has a fraction under the radical. So anytime your final answer ends up with a radical in the denominator or a fraction under a radical, we're going to need to fix that before we move on to the next problem. The process of removing the radical from the denominator is called rationalizing, because a radical that can't be simplified does not represent a rational number. So if we fix it so that the denominator does not contain a radical, we have made the denominator rational. So that's why we say we're rationalizing. Now, if the denominator only has one term, we can rationalize that by using the fact that a radical times itself removes the radical. So let's practice here. In example 13, it says rationalize each denominator. Basically, that just means we need to write it so that the denominator does not require a radical. So we'll be removing the radical from the denominator. Okay, 3 divided by square root of 7. This is a problem because we have a radical in the denominator. But the way to remove that radical from the denominator is to multiply that radical times itself. Now you can multiply the denominator by whatever you want, but whatever you multiply into the denominator, make sure you also multiply that same thing into the top, because any number divided by itself is 1. So here we're just multiplying by a big fancy 1, and we'll see what we get. So in the top, 3 times the square root of 7 is just that, 3 square root of 7. In the denominator, the square root of 7 times itself is going to remove the radical and give us just 7. So you see how now we have an expression that has a rational number in the denominator? This is called a rationalized denominator because the bottom number is rational. All right. If you took a calculator and you found a decimal equivalent for 3 divided by square root of 7, you would see that that decimal equivalent is the same as the decimal equivalent for this number. You can try it on your calculator and see that they are worth the same amount, but this is considered a better form, a more usable form, because it does not have a radical in the denominator. Now let's do the same thing on part B. We want to rationalize the denominator. So just like we did before, we'll multiply this denominator by square root of 5 because that would remove the radical. But because we're doing that to the bottom, we also must do it to the top. Okay, now in the top we're going to have 5 times the square root of 2 times the square root of 5. We'll use our product rule for radicals on the square root of 2 times square root of 5 here, and that's going to be square root of 10. So the top is going to end up being 5 times the square root of 10. In the denominator, we have square root of 5 times square root of 5, so that's going to be just 5. Now notice that this one can be reduced. So this 5 divided by that 5 is going to simplify, and our final result here will be just square root of 10. Now in part C we have negative 6 divided by the square root of 12. Notice that the square root of 12 is a radical that needs to be reduced. So we have two things that need to happen here. We need to reduce this radical, and we also need to rationalize so that the radical does not appear in the denominator. It does not matter which step you do first. You may do either step first. I'm going to simplify the radical first. So I'm going to think of 12 as 4 times 3. So I'm going to restate this as negative 6 over the square root of 4 times 3. Now you know the square root of 4 is 2, so the 2 is going to come outside the radical. Now in this case, that's really nice because I can see that 6 divided by 2 is going to reduce. 6 divided by 2 is 3. So when I do that division, the top then will be negative 3, and the denominator is still square root of 3. So all we did was simplify this fraction. 6 divided by 2 is 3 over 1, and that negative is still there. All right, now we still have the rationalizing to do. So we want to remove this radical from the denominator, so I'll multiply the denominator by square root of 3, but that means I also have to multiply the top by square root of 3. And now multiplying straight across, negative 3 times square root of 3 is just that. And in the denominator, square root of 3 times itself is 3. And now notice that we have negative 3 in the top divided by positive 3 in the bottom. So the 3's are going to cancel and just leave us with negative square root of 3. Now let's talk about how to rationalize a denominator that has two terms. If the denominator contains two terms, then what we have to do is multiply the top and bottom by the conjugate of the denominator. And that's just the same two terms, but with a different sign in between. The conjugate is the same two terms, but with a different sign in between. So this is going to work because you know that if you multiply a sum and difference of the same two terms, first times first gives you x squared, and the outer plus inner is going to add up to 0. Last times last is going to make minus y squared. And since both of these are squares, there won't be any radical left. So this is how we're going to have to rationalize denominators that contain two terms. Let's practice that on this pair of conjugates. So here we have square root of 5 plus square root of 3 times square root of 5 minus square root of 3. Okay, first times first, you know, is going to be square root of 5 times square root of 5. that's going to just remove the radical, so that will be 5. Because this is a sum and difference of the same two terms, the outer and the inner are going to add up to 0. And then last times last is going to be positive square root of 3 times negative square root of 3. That's going to be minus 3. And then 5 minus 3 is 2. So you see how, even though we started with all these radicals, because we're multiplying a sum and difference of the same two terms, the final result did not contain a radical. Okay, so here is example 14, and this just says rationalize each denominator, and you can assume that all variables represent positive numbers. Okay, 3 over 1 plus the square root of 2. I'm going to copy it here a little bigger so I can work on it. Because this denominator contains two terms, the only way to eliminate this radical is to multiply by the conjugate of these two terms. So I need to multiply this denominator by 1 minus square root of 2. And because I'm multiplying the bottom by 1 minus square root of 2, I also must multiply the top by 1 minus square root of 2. Now notice that I put everything in parentheses. That just makes it easier to remember what we're doing. The parentheses aren't technically necessary because the fraction bars act as a grouping symbol for us in this case, but I put them here so you could see what's going on. So in the top, we're going to be distributing the 3. 3 times 1 is 3, and 3 times negative square root of 2 is just minus 3 square root of 2. In the denominator, first times first is going to make 1. Outer and inner are going to add up to 0, because that's what happens when we multiply conjugates together. And then last times last is going to make negative 2, because a radical times itself removes the radical. Okay, now let's see what we've got. We've got 3 minus 3 square root of 2. That will not change. And in the denominator, 1 minus 2 is going to be negative 1. Now in this case, because the denominator is negative 1, let's go ahead and multiply both top and bottom by negative 1. That's going to just change the signs. It's going to give us negative 3 plus 3 square root of 2 for the top, and it gives us positive 1 for the bottom, which we do not have to write. Okay, in part B, we have 5 over 4 minus square root of 3. And of course, you see that we have two terms in the denominator. So in order to rationalize this, we need to eliminate this radical. And to do that, we need to multiply by the conjugate. So the conjugate of 4 minus square root of 3 is just 4 plus square root of 3. And that means we need to multiply a 4 plus square root of 3 into the top. Now distributing in the top, 5 times 4 is going to be 20, and 5 times square root of 3 is going to be just that. In the denominator, we have a sum and difference of the same two terms. So first times first is going to make 16. The outer and inner are going to add up to 0, and last times last is going to make minus 3, because remember, a radical times itself removes the radical. Okay, now we can't do anything about the top. That's as simplified as it can get, so that's going to stay 20 plus 5 square root of 3. Remember, we cannot add the 20 and the 5 because this 5 is being multiplied by square root of 3, and that takes precedence. Okay, in the denominator we have 16 minus 3, of course that's just 13. And now if you think about 20 and 5 and 13, they do not share any common factors, so we're not going to be able to simplify this any further, and this is our final result. In part C we have square root of 7 all over square root of 10 plus square root of 2. So of course you can see that we have two terms here, and so to eliminate both of these radicals, we're going to have to use the same strategy we used on part A and part B. So we'll need to multiply these two terms by their conjugate. So I need to multiply the denominator by square root of 10 minus square root of 2. But because I've done it to the bottom, I now must do the same thing to the top. And now we're going to distribute the square root of 7 through here, and we're going to use the FOIL method in the denominator. So here we go. Square root of 7 times square root of 10 is going to be square root of 70. Notice that there are no perfect square factors of 70 because this is just 7 times 2 times 5. So this radical cannot be reduced. And now we have square root of 7 times square root of 2, so that's going to make minus square root of 14. In the denominator, First times first is going to make 10 because a radical times itself removes the radical. The outer and the inner will add up to 0 because this is a sum and difference of the same two terms. And then positive square root of 2 times negative square root of 2 is going to make minus 2. Notice that we can't do anything about combining these two radicals in the top because the radicands are not the same. So these two radicals are just going to have to stay separate. But in the denominator, 10 minus 2 is 8. So we're going to end up with square root of 70 minus square root of 14 all over 8. Now I know that this has been a large section and there's a lot of material here and it's taken you a long time to work through it. And it's going to take you a little longer to work through the homework for this. But radicals are so important and they're going to come up all the time, just like fractions come up all the time. So you really need to get comfortable using them, and you can do it if you'll practice, just like you learned your exponent rules by practicing. So just hang in there and keep at it and just know that better things are coming.